This is Pondian from Erode Secondary Engineering College. Today we are going to discuss about the air standard cycles. Okay. Okay. The assumptions made in the air standard cycles are here air is considered as the working medium, and the air obeys the equation of state of an ideal gas. There is no change in the chemical composition during the reactions. The specific heats of the air are assumed to be constant irrespective of the temperature, and there is no change of phase of the working medium. So these are the assumptions made in all air standard cycles. So there are three air standard cycles are there, namely Otto cycle, diesel cycle, and dual cycle. But in this class, that we are going to discuss about the Otto cycle. So in the Otto cycle, it consists of four processes, namely the first process is the reversible adiabatic compression process. The next process is the constant volume heat addition process, and the next one is the reversible adiabatic expansion process, then the constant volume heat rejection process. So these are the various processes that constitute the Otto cycle. Okay, so in the Otto cycle, it is a cycle by which the IC engines, especially that spark ignition engines, are working. So it is an idealized cycle for spark ignition engines, and here we will see that we are seeing that the pressure, volume, and the temperature entropy diagram of the Otto cycle. Okay. So here the first one is the pressure volume diagram. So in that case, so initially during the suction stroke of an engine, the air and fuel mixture from the carburetor is entering into the engine through the intake valve. Okay, and that enters into the cylinder during the suction stroke. Okay, during the suction stroke. But since here it is an idealized cycle, we are considering only the air as the working medium. So we are assuming that the air alone is entering into the engine cylinder through the intake valve of the cylinder. Okay, and here at the point one, the pressure and temperature of the air that is entered into the cylinder will be the atmospheric pressure, and the temperature will also be the atmospheric uh, pressure, okay, atmospheric temperature. Okay, so since it is the least of the cycle, this is the least condition of the cycle. Okay, so and then this is the state 1 represents the beginning of the compression stroke. So during the compression process, the gases obey the governing equation of the adiabatic process. That means that PV power gamma equal to C. So since it is an adiabatic process, so there is no heat exchange between the system and the surroundings. Okay. So here during the compression process, the pressure increases and the temperature also increases, but there is a drop in the volume. Okay, from V1 to V2, V1 to V2, and the position 2 represents the end of the compression process, and also it represents the piston position at the top dead center in the case of vertical engine, or we can call it as an inner dead center in the case of horizontal engine. So this is the position number 2. So here the compression process is over, then the system undergoes the heat addition process. Okay, here heat is supplied from externally to the air, that is the compressed air, and because of that there is a pressure increase and also the temperature increase. Okay, pressure and temperature increases to the value of P3 and T3. Pressure increases and the temperature also increases. But here this heat supply process is taking place at the constant volume. So we can, from the diagram, PV diagram, we found that V2 is equal to V3. Okay. Then after the heat supply is over after the heat supply, then the hot air is undergoing the expansion process. So naturally during the expansion process there is a decrease in the pressure, decrease in the temperature, and there is an increase in the volume from V3 to V4. So the expansion, again, it is an isentropic expansion. The isentropic means it is a reversible adiabatic process. So during that process also there is no heat exchange. Okay, there is no heat exchange from the cylinder to the atmosphere. So there is no heat exchange, or from the atmosphere to the cylinder, there is no heat exchange. And then the process 4 to 1, it is a constant volume heat rejection process. So during the process, the heat is rejected from the system or from the hot air to the atmospheric, and because of that, there is a reduction in the temperature, okay, and a reduction in the pressure, and there is no change in the volume because here the heat rejection is taking place at the constant volume. So here the heat is rejected. That's why the arrow head is uh, from the system to the towards the ambient. Okay. So here it is given Q out also. So Q out or the heat rejected both are same. And here it is given Q in, that means that heat is applied to the system, okay, from the outside. So that's why here the arrow mark is put like that. And then this is the pressure volume diagram of the this Otto cycle, and this one is the temperature entropy diagram. So here, as we told, the process 1 to 2 is this reversible adiabatic process. So we know that for an reversible process, the change in entropy is given by, that is equal to dq by t, dq by t. So here ds is equal to dq by t, but since there is no heat exchange, so the value of dq is equal to 0. When the value of dq is equal to 0, then ds value will also be 0. That means that the entropy after the compression process will be equal to the entropy at the beginning of the compression process. That's why here 1 to 2, it is representing the constant entropy line, like a constant entropy line. So here the work is, because it is a compression process, so work is done on the system because here air is undergoing the compression process. So that air is considered as a system. So here the work is done on the system, then only the air can get compressed. Then the process 2 to 3 is a constant volume heat supply process. As we have discussed already, here there is an increase in the pressure and the increase in the temperature, but here it is taking place at the constant volume. Heat supply is taking place at the constant volume line. So this line represents that it is a constant volume line. Okay. So the heat supplied, it is, since it is taking place at the constant temperature, sorry, constant volume. So the heat supplied during that process is given by the formula M into CV into the T3 minus T2. So here why we have put a CV? CV stands for the specific heat at the constant volume. So since that the heat supply is taking place at the constant volume, so here we have taken into account that this was heat at the constant volume in order to find out the heat supply during this process. Then the next process is the 3 to 4. That 3 to 4 is the reversible adiabatic expansion process. So here also there is no heat exchange, okay, from the system into the surroundings or from the surroundings into the system. So heat exchange is equal to 0. So when heat exchange is 0, then there is no change in the entropy. So S3 will be equal to S4. Okay, but there is a drop in the temperature and as well as drop in the pressure that is taking place during this process. Then at the end of the expansion process, here the blow down process is taking place. Blow down means the hot air at the high pressure that is leaving out when the valve is open. So suddenly, okay, and here it is taking place at the constant volume. That means that the piston is at the, okay, piston is at the bottom dead center, and here when the, okay, when the here the that is the hot gear is moved, and then it is followed by the scrapping of hot gases from the engine cylinder into the atmosphere. So that is taking place. Okay. So this here during that the heat rejection process, the temperature is dropped and as well as the pressure is also dropped. But here the heat rejection process is taking place at the constant volume conditions. Okay. So this how we can plot that the temperature entropy diagram and as well as the pressure volume diagram for the Otto cycles. Then we will discuss that the analysis of the each and every process thermodynamically. So here the state 1 represents the beginning of the compression process. Okay, so the pressure, volume, and temperature at the state 1 it is given like okay accordingly. It is a temperature at the beginning of compression process in Kelvin, and the press P1 is the pressure at the beginning of the compression process in kilopascal, and the V1 is the volume at the beginning of the compression process in meter cube. And similarly, at the state 2, that the temperature, pressure, and volume is represented by the T2, P2, and V2. And here the state 2 represents the end of the compression process. Okay, end of the compression process. And we know that from the thermodynamics, that we know that the relationship between pressure, temperature, and volume, okay, for an adiabatic process. So we can write that T2 by T1 is equal to P2 by P1 whole power gamma minus 1 by gamma, that is also equal to V1 by V2 whole power gamma minus 1. So here this V1 by V2 is termed as a compression ratio. Okay, V1 by V2 is termed as the compression ratio, which is defined as the ratio of volume of the cylinder before compression to the volume of the cylinder after compression. Okay, so that is how we can define the compression ratio, and the compression ratio is denoted by the letter small r. So we can write that this V1 by V2 power gamma minus 1 as r power gamma minus 1, as r represents the compression ratio, which is given by the ratio of V1 by V2. So from this relationship, I can write that the value of T2 is equal to the T1 into r power gamma minus 1, and P2 is equal to P1 into r power gamma. Okay, then the next process is the thermodynamic analysis process of that is 2 to 3. The 2 to 3 it is the constant volume heat supply process. So here the state 2 that we already discussed what it represents. So state 2 represents the end of the compression process and the beginning of the heat supply process, whereas the state 3 represents the end of heat supply process. Okay, end of heat addition process. So T3, P3, V3 represents the temperature, pressure, volume respectively at the end of the heat addition process. And since that here the heat is applied at the constant volume, so it is denoted by the letters Q suffix S comma V. So why we have put a suffix S comma V is here the heat is applied at the constant volume. So to represent it, we have denoted as Q suffix S comma V. Okay, and the value is given in kilojoules per kilogram. And since that the heat supplied is taking place at the constant volume, so the heat supplied at the constant volume is given by the specified at the constant volume into that T3 minus T2. Okay, and since here it is a constant volume process, so we can make use of the equation of state at the state 3 and at the state 2. So from that we can give that P3 V3 by T3 is equal to P2 V2 by T2. So since that here the heat addition is taking place at the constant volume, so V3 is equal to V2. So from this I can write that P3 value by P2 is equal to the T3 by T2. So here that P3 by P2 is equal to R suffix P, that represents the pressure ratio, or we can also call it as the explosion ratio. Okay, we can also call it as the explosion ratio. And using that relationship, we can find that the value of T3 is given by T2 into RP, and that is also equal to, since T2 is already denoted as T1 into R power gamma minus 1, so that we have substituted here, so that I can get that T3 is given by T1 into R power gamma minus 1 into Rp. So similarly, we can write that the value of P3 is equal to P2 into Rp. So P2 is given as P1 into R power Rp power gamma, sorry, R power gamma. So here it is written P1 into R power gamma into that Rp. Okay. So this way we can find out the temperature at the end of the heat supply process and the pressure at the end of the heat supply process. And once that the temperature at the end of the heat supply process is known, then we can substitute this value in this formula so that we can find out the heat supplied at the constant volume process. Okay. Then the next one, it is the thermodynamic analysis of the that reversible adiabatic expansion process, or we can also call it as the isentropic expansion process. So here the state 4 represents the end of the expansion process. So similarly, accordingly, the temperature, pressure, and volume is denoted as T4, P4, and V4. So since this is also an adiabatic process, so we can use the same relationship for this process. So it is given by the T4 by T3 is equal to P4 by V3 power gamma minus 1 by gamma, that is equal to V3 by V4 power gamma minus 1. So here from the PV diagram we can find that value of V3 is equal to V2 and V4 is equal to V1. So it is V2 by V1 power gamma minus 1. And we know from the thermodynamic process 1 to 2 that V1 by V2 is equal to the compression ratio R. But here it is V2 by V1. So we can write it as 1 by R power gamma minus 1. So from this relationship I can get the formula for temperature at the end of the expansion process T4 is equal to that T3 divided by R power gamma minus 1. And we know already what is the value of T3. So T3 is given by T1 into R power gamma minus 1 into the value of Rp and divided by this R power gamma minus 1. So R power gamma minus 1 is present both in the numerator and as well as in the denominator. So they are getting cancelled, so that we can give that the value of T4 by the product of Rp into T1. Okay. So similarly, we can get the relationship for the pressure at the end of the expansion process. So P4 is equal to that P3 divided by R power gamma. So it is given by that P3 is given by Rp into P1 into R power gamma. So it is divided by R power gamma. So R power gamma and R power gamma get cancelled. So we can get that the value of P4 is given by Rp into P1. So using these three thermodynamic analysis of the process, so we can get the temperature, pressure, and volume at all the salient points. So now the process 4 to 1 that represents it is a constant volume heat rejected process. So since that we know all the temperatures, so we can directly go and write the formula for the heat rejected at the constant volume, and it is given by the product of the specific heat at the constant volume into the temperature difference T4 minus T1. So using that we can find out the heat rejected at the constant volume. So once this is found, if all the temperatures are known, then we can go for finding the efficiency of the cycle. So efficiency of the Otto cycle is generally any efficiency of the heat engine. It is given by the formula. It is the net work to that the heat supplied. It is given by the ratio of net work to that the heat supplied. And since here the system undergoes a cyclic process, so from the first law of thermodynamics we know that the net work is equal to Q net. Okay, Q net. So using that relationship, I can write what is Q net. Q net means, so since in this process the heat is applied during the constant volume, okay, during the process 2 to 3, and similarly that heat is rejected during the process 4 to 1. So the net heat is equal to the difference of heat supplied and the heat rejected. Okay, so from that we can find out the net heat supplied or net heats. Okay, so that we can substitute in this formula. So efficiency. So efficiency is given by that QS minus QR divided by the QS. So since that the QS is available both in the numerator and in the denominator, so we can take it commonly outside. So it can be written as 1 minus QR by QS, and we know that already. So what is QR and what is QS? So that formula is substituted here. So we can get that after substitution and simplifying, we can get that the efficiency is given by 1 minus T4 minus T1 divided by T3 minus T2. So if all the temperatures are known, then we can make use of this one to find out the efficiency of the cycle. Okay, and since we have already developed the equation, that is T4 in terms of T1 and T3 in terms of T1 and T2 in terms of T1, so we can substitute that values here, and after substituting them, then we can get the equation as efficiency eta is given by 1 minus 1 by r power gamma minus 1. Okay, so if the compression ratio alone is known, then we can find out what is the efficiency of the Otto cycle. Okay, so in this Otto cycle, the compression ratio range is from 6 to 10. Okay, from 6 to 10. The next one is the mean effective pressure. So what is mean effective pressure is? It is the pressure that is assumed to act on the engine throughout the cycle of operation, as the in-cylinder pressure varies continuously from minimum to maximum. Yes, because we know that at the end of the suction process, the pressure inside the cylinder will be equal to that of the atmospheric pressure. And similarly, during the compression process, its pressure is increasing from minimum to that the maximum. And again, since that the heat is added at the constant volume process, so that causes the increase in the pressure. So the maximum pressure is obtained at the end of the heat supply process. And again, during the expansion process, the pressure is getting reduced. And again, during the blowdown process, it's further reduced. Okay. So here, since in the in-cylinder pressure varies continuously from minimum to that the maximum. So when such is the case, then to what pressure we have to design that engine. So in that cases, we need to find out an suitable parameter. So that suitable parameter is nothing but the that mean effective pressure. So mean effective pressure is an hypothetical pressure, that is an average pressure that is assumed to take place inside the cylinder throughout the cycle of operation. So it is mathematically it is given as the ratio of cyclic net work to that the swept volume. Okay. So from this we can find out that what is the mean effective pressure. So here I have written that the formula. So mathematical expression, that is mean effective pressure is given by W net divided by this swept volume. Okay, and here we know that for a system undergoing the cyclic process, the W net is equal to Q net, and that Q net is given by Qs minus Qr. So divided by that Vs. So then again we know that. So what is the mean effective pressure? So it is given by, okay, it is given by the formula, that is Cv, because heat supplied is given by Cv into T3 minus T2, and minus Qr is given by the formula, that is Cv into that T3 minus T4 minus T1. So using that process that we can find out the numerator, it is divided by the denominator Vs. Okay, denominator Vs. And here that Vs represents the swept volume. So that Vs can be given mathematically as the difference in the volume when the piston is at the bottom dead center to that the different volume of the cylinder, and the piston is at the top dead center. So the piston at the bottom dead center is denoted as V1, whereas the volume at the top dead center is denoted as V2. So we can write that Vs as V1 minus V2. And again, from the analysis, we know that it can be written that Vs can be written as 1 minus V2 by V1, and that V1 can be taken commonly outside. So V1 into 1 minus V2 by V1, and here that V2 by V1 is nothing but 1 by R. So on taking that the common denominator, then we can write that it is V1 into R minus 1 divided by R. So that value has been substituted here. Okay, that value of Vs is being substituted here, and here again the formula for that is T4, T3 value and T2 values have been substituted here. And since that the Cv is present both the term in the numerator. So that has been taken outside. And we know that the formula, that is a specific heat difference in specific heat Cp minus Cv, that is equal to R. So if all the terms in the equation is divided by Cv, then we can get that Cp by Cv is equal to gamma minus Cv by Cv equal to minus 1. So that is equal to that R by Cv. So gamma minus 1 is equal to R by Cv. So from that we can find that what is the value of that, okay, so Cv value, because we got to replace that Cv by that R by gamma minus 1. So that I have substituted here. And since in this term that the T1 is present in almost all the terms, so that has been taken outside. So the numerator is written as RT1 by gamma minus 1, and the other terms have been kept here. Okay, and here the values of Vs is also being substituted here. And again in this equations that RT1 by gamma, okay, gamma minus 1, and here that V1 is also there. So RT1 by V1 we can get, okay, we can get that. So RT1 by V1 is given by the term P1. So that has been substituted here, and the other common terms that has been noted. So we, from this we can find that the term for our equations for the mean effective pressure. So mean effective pressure is given by the P1 divided by gamma minus 1 into R by R minus 1, and it is multiplied by that R P minus 1 into that R power gamma minus 1 minus 1. So using that relationship that we can find out the mean effective pressure of the Otto cycle. Okay. So now let us solve one of the problem on the Otto cycle. So a spark ignition engine working on the principle of Otto cycle has the cylinder dimensions as bore equal to 74 mm and a stroke equal to 90 mm. Compression ratio is 9:1. The condition of air at the beginning of the compression are 101.3 kilopascal and the temperature 20 degrees Celsius. The maximum temperature in the cycle is given as 1970 degrees Celsius. So determine the pressure, temperature at the all salient points, the thermal efficiency and the mean effective pressure. So this is the, now we will write the given data. So that is bore is denoted by the letter D. So D is equal to 74 mm. So but we have to substitute everything in meter. So 74 mm is equal to 0.074 meter. And the stroke is given as 90 mm. So that is equal to, when you convert into meter, it is 0.09 meter. And it is given that the compression ratio is given as 9:1. So I can write that R is equal to 9:1. Then it is given in the problem that the pressure at the beginning of compression stroke is given as 101.3 kilopascal. So that has been taken, and the temperature at the beginning of the compression stroke is 20 degrees Celsius, but we got to convert that into Kelvin. So it is added with the 273, so that the T1 is equal to 293 Kelvin. And here it is given the maximum temperature in the cycle is 1970 degrees Celsius. So we have to find out that from the TS diagram, okay, from the temperature entropy diagram. So we found that the maximum temperature is obtained at the state 3. So we can, that maximum temperature is also equal to the temperature at state 3, that is equal to 1970 degrees Celsius, that is equal to 2243 Kelvin. So after finding all these things, then we can, we got to determine the values. Okay, we got to find out that the temperature, pressure at all salient points. So for that, we know already the relationship T2 is given by the T1 into R power gamma minus 1. So we have given that it is, okay, that is the value of R is 9. Okay, so 9 power gamma here, for here the value of gamma is equal to 1.4. So T1 is equal to 293 Kelvin into that 9 power, okay, 9 power 0.4, that gives that the value of 705 points, okay, 705.6 Kelvin. It is the temperature at the end of the compression process. Okay, so similarly here we can find out the pressure at the end of the compression process. It is given by the formula, that is P1 power or P1 into R power gamma. So again I told that the R value is 9 and the gamma value is 1.4. So P1 is given as 101.3 kilopascal. So using that formula, we can find out that the pressure at the end of the compression process, that is equal to 2195.578 kilopascal. Then after finding that the values, then here already the value of T3 is given. So using the formula for the heat supplied at the constant volume, we can find out that it is given by the formula that is Cv into that T3 minus T2. So T3 value is given and the T2 value is given. And what is Cv is the specific heat at the constant volume. For air, it is equal to 0.718 kilojoules per kilogram. So substituting all the values, that we can find that the heat supplied at the constant volume is given as 1103.8532 kilojoules per kilogram. And since that T3 value is given in the problem, so we know that the formula for RP, so RP is nothing but P3 by P2, that is also given by T3 by T2. So we have to substitute the values of T3 and T2. So we get that the value of RP is equal to 3.1788. So using that formula, we can find that the value of P3. So we know that P3 is given by RP into P2. So already we found that the value of P2 here. So it is multiplied by the value of RP. So using that, we can find out what is the value of P3. Okay, and similarly, since the T3 value is given, so that is not necessary to find again. And then P4 and T4, again using the relationship, that is P4 is given by that P1 into RP. Okay, using that, we can find out the value of P4. And similarly, the value of T4 can be found by, it is T1 into RP. So using those formulas, that we can find out the temperature and the pressure at the end of the expansion process. And if the pressures and the temperatures are known, then we can find out that the heat is rejected at the constant volume during the constant volume heat rejection process 4 to 1. So it is given by, or it is found to be that 458.363 kilojoules per kilogram. And the formula used here is again that that is Cv into the T4 minus T1. So after determining all these values, then we can substitute in the formula to find out the efficiency. So as we know that the simple formula for efficiency of the Otto cycle is 1 minus 1 by R power gamma minus 1. So R value is 9, gamma value is 1.4. So that has been substituted here and found that we can, the efficiency as the 0.585. Okay. Now we can cross check whether the obtained value is correct or not. This seems that we already found all the temperatures, so that temperatures have been substituted here to determine that efficiency. So here is also we found that the efficiency is equal to 0.585. So we have cross verified the efficiency. So what we have found is in this formula is correct. Okay, and also that this efficiency also gives that the temperatures that we have found is correct. Okay, at different saline points. Then we can find out that the mean effective pressure that is given by the formula. Okay, that we already know it is a ratio of that the W net by Vs. So W net is equal to Q net for a reversible process. So we can write that Q net is equal to Qs minus Qr. So it is written as Qs minus Qr divided by Vs. So but we already found that the value of Qs and Qr, but the value of Qs and Qr or in the unit of kilojoules per kilogram. Okay, and here is also it is in kilojoules per kilogram, but the value of Vs is in meter cube. So if you substitute the values here, so in the numerator that you can get kilojoules per kilogram, whereas in the denominator you can get only that the meter cube. So the kilogram will not get cancelled. So that we need to find out either the specific volume, or we got to find out that the heat supplied per kilogram of the substance. So for that purpose, I have to find out the mass of the substance. So from the ideal gas equation of state, we can find out that the mass of the substance can be given by that P1 into V1 divided by that R power R in, okay, divided by R into T1. So we know that from this formula that we can find out that this mass. But again here in the problem they have given only the swept volume, but the V1 value is not given. So we already know that the value of Vs is given as that V1 into that R minus 1 divided by R. So it is rearranged that. So V1 is equal to Vs into R divided by R minus 1. So using this formula, we found that the value of V1 as that 0.00043575 meter cube. So this value of V1 is substituted here to find out the mass of the substance M in kilogram. Okay, so that value of M is found to be that 0.000525 kilogram. So after finding out this value, then we can already found the value of Vs. Okay, or here if you want to substitute that the specific volume, okay, specific displacement volume, then we can find by it is capital Vs divided by mass. So it is found to be, okay, it is found to be that 0.73714 meter cube per kilogram. So from this now we can get that the numerator and the denominator in the same units. Okay, it is kilojoules per kilogram and it is meter cube per kilogram. So kilogram may get cancelled. So only thing is that you will be getting kilojoules per meter cube. So kilojoules is nothing but kilo Newton meter, okay, divided by meter cube. So meter in the numerator and meter cube, okay, in the denominator. So that 1 meter is get cancelled. So the resultant term is kilonewton per meter square. So that kilonewton per meter square is nothing but kilopascal. So the values have been substituted here and found that the mean effective pressure, okay, of the Otto cycle given is that 875.6684 kilopascal. So with this example, okay, we found that how we can find out the efficiency of the Otto cycle and also that the mean effective pressure of the Otto cycle. Okay, so with that the thermodynamic analysis and the details on the Otto cycle is over. So I hope all of you might have understood the concept of the Otto cycle. So in the next class that we are going to say that the okay, the again different determination of efficiency and the mean effective pressure of the diesel cycle. Okay, in the next class. Thank you very much for your presence.